Good morning, everyone, or good afternoon, everyone. So now we are starting the second day of the International Conference on Quantum Computing 2021, the ICQC 2021. Today we will start with an industry session. And also the industry session will start with two invited speakers who are leading the quantum computing research in the world. The first speaker will talk about the ion trap-based quantum computing. The second speaker will talk about the superconductor-based quantum computing. And after the invited speakers, we will have 4 speakers from the companies, industry, who are actively doing real commercialization of the quantum computing. And in the end, we will have a panel discussion where all the speakers, including the invited speakers, will join and discuss about the current status of the quantum computing industry and the research development. Okay, now I'm really happy to introduce Dr. Jungsang Kim, who is a professor in Duke University and also CTO of IonQ. Jungsang Kim graduated Seoul National University and then got his PhD degree in Stanford. He worked as a research staff in Bell Lab, and then he worked as a professor in WE in Duke University. He founded IonQ, and now he is going to explain about all his adventures through the ion trap quantum computing. Please.
All right. Thank you very much. I'm very happy to be here, actually to be able to be here in person. I'd like to thank the organizing committee for putting together this wonderful meeting. Today I'd like to share some of the progress we have made, and this work I'm going to present is a mixture of work that was done in our university research at Duke University and University of Maryland with my longtime collaborator Chris Monroe and our team. And also, I'll share some of the progress we've been making at IonQ in our effort to commercialize ion trap-based quantum computers. So let me start out by pointing out what is a quantum computer. And this is a quote from a longtime colleague and Nobel laureate, Professor Bill Phillips, who once said, "A quantum computer differs more from a classical computer than a classical computer differs from an abacus." And the recognition here is that an abacus and a classical computer, they still treat information as a classical object. And the way that quantum computers treat information as a quantum object is so fundamentally different. You can say that the difference between the bottom two, the abacus and a classical computer, is just a matter of technology and engineering, whereas the difference between a classical computer and a quantum computer is really a matter of fundamental difference. So with that in mind, and I think one of the things we wanted to highlight is when we build an object that is so different, it doesn't have to look very much like a classical computer at all. And I'd like to make sure that we keep that in mind. All right. And then I think the audience is quite familiar with quantum computers, I would assume. So I'll skip a lot of the very fundamental basics, but maybe think about what are some of the elements that are needed to build quantum computers. And you obviously need qubits. These are the fundamental units of quantum information. And unlike a classical bit, which represents just 0 and 1, a quantum bit or qubit has to represent a superposition. And also, unlike classical information, multiple qubits can be in an entangled state where there is a fundamental correlation. And this actually is shown as an example of this is shown here in psi1-2, where it cannot, the state of this two-qubit system cannot be broken down into a product of independent phi1 and independent phi2. So that's the basic element. And then, of course, we think about logic gates. In order to actually process information, we have to have a set of rules that define the output given the input. And classically, we know what works here. We have these NAND gates and NOR gates and logic gates that actually processes the information. And of course, quantum mechanically, we have a similar objects like single qubit gates and a multi-qubit gate. In this example, a control NOT gate. The difference is that the quantum logic gates has to be reversible, so that we don't actually lose information along the way. And there can be very large numbers of single qubit gates, unlike the classical case. So these are the things that we typically think about. But there is actually one very, very important element to this. If you just think about the foundational components, you may think of this as a sufficient condition, but that is actually not the case. In classical computers, if you look at a computer chip, and this shows the cross-section and basically an etched version of it, we typically found out that there is a very simple, like a single layer of transistors on the surface of a silicon substrate, but there usually is a dozen layers, a very large number of layers of wires that we draw. Okay? And that is because in order to actually process information in the way that we want, we not only locally process information, but we also have to transport information from one location to another. And it turns out that the way that we move information around is what actually provides the complexity of the computation we can actually perform. Okay, so if you are a device physicist, we think about transistors and logic gates. But if you're a circuit designer, you just think about how to connect things up. Okay, you spend all of your time building connections on the chip. So transporting qubits between logic gates turns out to be an extremely important element. In fact, if you look at the number of devices that we build on a classical computer, we build a lot more wires than we build transistors. And that is probably going to be the case for quantum computers. In order to actually process and do a computation, there's a lot of communication that needs to happen for qubits. And building a high density of highly connected quantum devices is going to be one of the main challenges as we think about processing machines. All right. So with that, I'd like to then, with that notion, I'd like to dive into Trapdown quantum computers. Oops. All right, so here we see an example of Ytterbium 171, and that's the qubit that we actually use for in our quantum computers. And the reason we use that is simple. It actually has a nuclear spin of 1/2, and it behaves like it has a single electron orbiting around the nucleus when we run the operations. So it looks very much like a hydrogen atom, and that actually gives you the simplest ground state. That is actually non-trivial. What that means is we have a ground state that is made up of 2 spin levels of electrons and 2 spin levels of nucleus. It has a nucleus spin of 1/2, and the combination of that splits the energy level into a singlet and a triplet state. And if you pick these 2 energy levels in the middle, it turns out that the frequency difference of that level is extremely well defined. Okay, so now you ask the question, what are some of the fundamental limits of a qubit represented by this system? So as you know, a qubit is a linear superposition of a 0 and 1 state, these 2 states, and the coefficients of that linear superposition is given by given by 2 complex numbers. And because of the normalization condition, at the end of the day, a qubit state is represented by 2 real numbers. One is this azimuth polar angle theta, and then another one is this azimuthal angle of psi. And that actually allows a qubit state to reside on the surface of a unit sphere called the Bloch sphere. So usually you think about this theta as the amplitude between the 0 and 1, and this phi as the phase between the 2 quantum states. So when a qubit degrades, it usually degrades because theta is changing, which is basically a weight or the population between the 2 states is changing, or when the relative phase between the 2 is changing. Now, it turns out that when you look at the ground state of a hydrogen atom like this one, or hydrogen-like atom, the time it takes for theta to change, which is the spontaneous emission rate, turns out to be really long. Okay, for a hydrogen atom, it's estimated to be a few million years, okay? Which means that it's just so long that you won't be able to measure it. And for ytterbium, it's also expected to be longer than many thousands of years. And I think the only reason that it will actually change is if it collides with another molecule that's nearby. And therefore, the T1, or the spontaneous emission related decay of the qubit state is really limited by vacuum technology and not by any fundamental science. The second issue is the notion of this phase, relative phase phi. And in a quantum mechanical system, if you have two energy levels that have an energy difference, then there is a trivial rotation. There is a phase rotation that's given by e to the I omega t, where omega is the energy difference between the two levels divided by h bar. And when that frequency is extremely well defined, then you know exactly where that phase is. But if the frequency actually fluctuates over time, then that accumulates a phase noise, and that actually leads to dephasing. So any dephasing in a qubit, in a practical sense, is actually determined by the uncertainty of the energy level difference between the two qubit states. Okay? And in ytterbium, this actually is very accurate. We know this energy level difference up to about 9 digits or 10 digits or so. And therefore, without trying very much, we actually have a coherence time, or T2 time, of about a second. And with a little bit of effort, meaning like shielding, magnetic field shielding, and isolating and improving the clock, the classical clock, we can actually get them to multiple hours. Actually, Professor Ki-won Kim's group at Tsinghua University have recently demonstrated a multi-hour coherence time for this exact qubit. But it turns out that the question of how well we can determine this frequency is a very fundamental one. It turns out that if you replace ytterbium with another atom called cesium, with a similar hypofine splitting, then this separation of cesium hypofine level, 9.192631770 gigahertz, turns out that number is exact. Meaning that hypofine atomic state is the most stable frequency reference we can find. So the international community, scientific community, has decided that we're going to define our frequency based on this as an absolute reference. So by definition, if you had a cesium clock or cesium qubit, then the coherence time is infinity, because that's your reference by which you measure the decoherence or the frequency reference. But given that the ytterbium has exactly the same atomic physics, you might as well pick ytterbium as your frequency reference. Then, again, in principle, your qubit does not dephase. And now you're only limited by technical noise, like magnetic field noise, and your ability to synchronize your clock to this atomic reference. So what this means is, when left alone, if you can isolate this atomic qubit extremely well, then your T1 and T2 for the qubit can be made arbitrarily long. Okay? And that is actually a very unique property of an atomic hypofine qubit. And I think that's one of the fundamental reasons we believe that this is the best qubit you can find if you're only worried about quantum memory storage. Now, that does not mean that you can actually build perfect quantum computers quite yet. It turns out that when you start to do operations on them, then you're limited by other technical imperfections. And here, I'm going to just summarize what some of those imperfections are. So when you initialize a qubit, we use a process called optical pumping. And the fundamental atomic physics says, for this qubit, your fidelity or your error rate is limited to about a part in 10 to the 6, meaning 1 point a part in a million. And you can routinely achieve this because there's no other mechanism to degrade this process. When you're doing a qubit measurement, we use what's called a resonance fluorescence. It means that one of the qubit states, when illuminated by a very narrow line laser, is going to scatter a bunch of photons, whereas the other state will not. And by looking at whether the atom is bright or dark when you're shining certain laser beams, you can distinguish the two states. And this can be done with high fidelity, where the errors are typically in the 10 to the minus 3 to 10 to the minus 4 range. And these were demonstrated experimentally and rather routinely achieved in commercial quantum computers today. Single qubit gates are driven by what's called the off-resonant Raman transitions. And here, still a very high fidelity gate can be demonstrated, limited by the spontaneous emission properties of the atom and residual laser noise in the system. And here we expect a high gate fidelity of 10 to the minus 4 in the 10 to the minus 4 range. We should be able to do that routinely, and indeed many of the commercial quantum computers actually accomplish that. And I think the fundamental limit is the 10 to the minus 5 range. I haven't seen a whole lot of commercial computers achieving that, but 10 to the minus 4 is something that is routinely done today. And then 2 qubit gates is done by state-dependent force from Raman transition, and this is probably the most tricky one. And that's because we actually not only use the internal states of the atom, but you also have to use the motional state of the atom to operate this gate. And that's where all the difficulties arise, because that motional degree of freedom is not as stable and perfect as the internal degrees of freedom for the atom. So the gate fidelity here are typically in the 1% range. People have been pushing this to about 10 to the minus 3, meaning 0.1% range. Some commercial systems are starting to operate in that range. And I think some of the fundamental limit posed by this in the 10 to the minus 4 or 10 to the minus 5 range. All right, so what this means is we can actually have a very high performance system that's potentially available. So that's the fundamental physical system. So now let's think about how we build practical quantum computers with trapped atomic ions. So this is actually a picture of my colleague Chris Monroe's lab taken in 2016. That's roughly when we started IonQ. And this is what a typical ion trap quantum computing experiment used to look like. Right? It still looks like this in many laboratories around the world. You typically have a lab with a big optical table, and we have a bunch of lasers and optical components assembled one by one, typically on an optical table, and a full rack of equipment that's needed to control these experiments. And because the stability of this optical system is actually not very stellar, it takes a lot of time and effort for graduate students and postdocs to maintain this experimental setup. And that's one of the reasons why people thought, design trap experiments, it's very hard to imagine this becoming a commercial system. So in 2016, we started a project funded by IARPA and made an effort to see if we can take this and turn it into more of a commercializable system. Okay, so we took apart the building blocks, such as the vacuum chamber and the lasers. Gate laser, this is like the high power laser that drives all of our logic gates. The illumination module, this is how we deliver those beams to the ions and a bunch of other components. And then we try to turn them into subsystems that can be assembled to build an ion trap quantum computer. And by the time we came up with this design, we thought maybe we can actually start to build this commercially. So we started IonQ, and in 2017, we started building commercially viable quantum computers using this as the blueprint. So the qubit technology that we use it starts with an ion trap, and this trap specifically uses a technology that was developed in collaboration with Sandia National Labs. And that trap is made out of silicon, and it actually is about 1 centimeter in size. And that bow tie shape is there just to make sure that we can bring laser beams in with a certain amount of numerical aperture to control the lasers. The blue dots that you see on top is a blown up image of 80 individual atomic ions. And here the separation of these atoms are about a few microns, maybe 3 to 5 microns. So 80 atoms only occupy about 0.5 millimeter of size. So this is really a small area on which all of our qubits are trapped, and all of our quantum operation actually happens in that space. The rest of it is just there to support the actual interaction between the lasers and the qubits. So inherently, our qubits are extremely compact. All right, so this actually shows a video of how we can manipulate these qubits on our systems. So you can see that at the bottom we have a loading zone, and that's where we load individual atoms one by one. And we actually, in this example, we show you how we build up a quantum register of 23 qubits as an example. So we load one ion, we move it into the quantum zone. Once we have enough, or exactly the number of ions we want, we stretch them out, and now they're evenly spaced atomic chain that is ready to be used as a quantum register. And the way we manipulate it, we start from a single laser beam that can split into, in this example, 32 ways. And then each of these laser beams are aligned onto the atomic chain. And then when you start the operation, we initialize it by shining certain laser beams and optically pump all the states into the zero initial state. And then as we run the gates, we turn on these manipulation laser beams that can execute single qubit gates, 2 qubit gates, and in some cases multiple 2 qubit gates at the same time. And the actual gate operation is entirely determined by designing these laser pulses. And because all of these ions are interacting through Coulomb interaction, you can actually pick arbitrary pairs in the system and then actually operate quantum logic gates on them. And when we're all done, we shine this detection laser beam, and some atoms will glow, others will not. Those that glow are read out to be a qubit state 1, and those that don't glow are read out to be a qubit state 0. All right, so although we start with a linear chain, it turns out that we can actually execute 2 qubit gates on arbitrary pair of qubits in a relatively long chain. And this actually gives you what we call a all-to-all connectivity, meaning this is an example of 11 qubits, and the top figure shows that in an 11 qubit ion trap quantum computer, you can actually pick arbitrary pairs of qubits and execute 2 qubit gates between them. And here we show an example of 11 qubit system. In 11 choose 2 is 55 possible gate pairs, and we can actually execute all of them. And it turns out that the time it takes to run the gates and the fidelity you can accomplish is actually fairly uniform. Okay? And that actually gives you a huge advantage when it comes to executing an actual algorithm. So let me show you a study of how that was done. This is a paper from Professor Margaret Martinozzi's group in Princeton University. And she's a computer architect, and she actually has had access to IBM, Rigetti, and a 5-qubit University of Maryland Trapdown quantum computer prototype. And she and her team ran a whole bunch of algorithms, benchmarking algorithms, that actually, and then compared the performance between them. And because she only had access to 5 qubits of ion trap quantum computer, when there were algorithms, BV stands for Bernstein-Vazirani algorithms that require more than 5 qubits, they could not execute it on this specific ion trap quantum computer. However, now let's move on to some of the other examples. This is a 2-qubit hidden shift algorithm, and this is a quantum Fourier transform algorithm. It turns out that these algorithms are very local, meaning you don't need a lot of connectivity. You don't have to transport qubits a lot in the middle of the computation. And for those types of algorithms, you can see that most of these quantum computers actually operate pretty well. You still see a little bit of a higher fidelity on trapped ion quantum computers, just because the fidelity was a little bit higher. But most of them succeeded with a pretty decent probability. However, when you move on to other algorithms where a lot of transportation of quantum bits were required in the middle of the computation, you can see that these quantum computers with limited connectivity, the algorithm performance starts to suffer. You can see that the trapped ion is, the probabilities are high on all of these algorithms, just because you never have to translate a single 2-qubit gate into multiple 2-qubit gates because of the lack of connectivity. Since we have put IonQ quantum computers on the cloud last summer, we're starting to see a lot of studies where people are running same algorithms on IonQ machines and comparing them with other systems. Here, I've done a quick search on the archive, and there are several papers that have come out in the last couple months just comparing performance of IBM machines with trapped ion quantum computers from IonQ. Here, this example is, again, the details are not, I'll refer you to the papers, but here they run some quantum games, and you can see that the 2 ion trap quantum computers from IonQ and Honeywell performs quite a bit better than the IBM machines that they have looked at. Here they have done some QND measurements, quantum non-demolition measurements experiment, and compared IBM systems with IonQ. You can see that the first graph is error. So blue is IonQ errors, and the orange and the yellow are errors from the IBM machines. The second graph shows fidelity, meaning, and you can see that the fidelities for IonQ systems tend to be very high compared to other systems. And here on the right, they do some generic benchmarks. You can see that IBM machines, and this it's hard to read, but this actually shows it's some performance metric, and where higher is better. You can see that the IBM machines are kind of down here. It's a class of machines, and IonQ systems are up here in a qualitatively different manner. So what we're seeing is these ion trap quantum computers, when an actual algorithm is run, they tend to run consistently better than other quantum computers available on the cloud. And this is based on our first generation system. Our second generation system is coming up and running, and the performance is going to be substantially better than what we have seen in the past. All right, so with this kind of performance, we can actually start to run some interesting near-term quantum algorithms. So we have done some of this work, and I think many of the speakers in this following session is going to talk about some of these. So I'm going to be very brief on this. But there are some on quantum machine learning, there are some fundamental advantages that are starting to be proven using quantum machine learning compared to classical. And these learning complex patterns, there are some exponential gains that have been demonstrated or proven, predicting in certain worst case errors. And quantum correlations have been used in generative modeling. So these are some of the papers that's been coming out over the last few months, and it's actually, there's a lot more coming out pretty regularly. And it looks like the area of quantum machine learning is evolving into a pretty rich opportunity for quantum algorithms. And of course, in quantum chemistry and material studies, people have studied variational quantum eigensolvers for energy estimation, and more complex problems such as quantum simulation of dynamics and many-body phenomena are starting to get explored. And of course, there are optimization problems, quantum approximate optimization algorithms, QAOA, are starting to attract interest from the industry. So, these are some of the interesting application areas. I'd like to give you a few examples of machine learning and quantum chemistry work that was recently done with IonQ machines in recent days. So one example is this work we have done with QCware, where we're trying to do classification. And here we use two different data sets. One is the iris data set. And this is just a picture of a bunch of iris flowers. And there are three different categories of flowers that there are. So we use a bunch of images to train the quantum machine. And then we look for classification of a given picture. The other thing we have done is this Mnist database of handwritten characters, or in this case, handwritten digits. See if we can train these and then identify what digits are being written. So the way we do this is you first fit your model, you find centroids of these feature space, and then you classify your images into, in this example, 3 different categories. Okay? And then, given a new data, new image, you predict the labels of this new data using a quantum algorithm. Okay? In this example, we have a data loader circuit, which is very efficient. It's actually only logarithmic depth, but the logarithmic depth is achieved only because we have an all-to-all connectivity. You can see that this B and the S is basically a 2-qubit gate that we're applying, and the distance between the 2 qubit gates can vary. And that's actually why we could actually realize this in a logarithmic depth. And then the estimator is actually a back-to-back application of such a circuit. And then we've also come up with some error mitigation techniques to actually discard some unwanted data where clearly an error has happened. Now using that, we now see some performance. You can see that this is actually your 4-qubit quantum computer that is actually differentiating or identifying, classifying images of irises. Okay, this is the real pictures that we're classifying here. You can see that classical classifier error is shown by the dotted line, and the quantum error is a little bit higher. The raw data is pretty bad, but by error mitigation, we can actually do a little bit better. You can see that the error here is a little large because this red class of pictures, one of the types, if you look at the pictures, the first one is very distinct from the second and the third, meaning the second and the third, there's a lot of room for confusion, even for classical algorithms. So you can see that on the right, the red is very distinct, but the blue and the green have a little bit of overlap, and it is a little bit difficult to perfectly isolate the pictures, but the quantum machine learning algorithm is doing a pretty good job. The next example is using Mnist database. In this case, we are differentiating with an 8-qubit quantum algorithm, differentiating between 0 and 1. We can do that really well. You can see that this diamond is a classical error. Blue is quantum algorithm without error mitigation, and the orange is quantum algorithm with error mitigation. You can see that for 0 and 1, we can distinguish them really well. For 2 and 7, they actually look a little bit more similar, so there is a little bit of error, even for classical algorithms as well. And when it comes to differentiating all 10 characters, the quantum algorithm is doing pretty well. You can see that this orange, error-mitigated quantum algorithm, the performance is actually comparable to the best classical algorithms. Now, there are other examples. In this case, we work with Zapata, and hopefully Chris may talk about this a little bit later. But here what we have done is we did the inverse problem. We used quantum computers to generate these handwritten digits. So these digits that you see on the right, these are actually generated by an 8-qubit quantum computer using IonQ machines. And some of the metrics that they have looked at, in this case, this thing called the inception score, you can see that in some cases, the quantum computers actually produce better looking handwritten digits than classical algorithms can. This shows another example where a group at Volkswagen used the cloud access of IonQ machines to solve a binary paint shop problem, which is an optimization algorithm. All right, so what this is showing is we're starting to get some really interesting progress in using realistic algorithms, and although they're still very small, these realistic algorithms can actually be run on a quantum computer, and pretty meaningful results can be generated. But these are still very small toy problems. The question is, can we actually extend this into something that is much more challenging for classical computers? And I think there's a lot of room for doing interesting work on that space. All right, so in the last few minutes I have, I'd like to kind of look ahead and say, okay, we built this quantum computer, it's on the cloud, they run 24/7, they run reasonably well, the connectivity gives you pretty decent performance in many algorithms, but where are we headed? How do we get to much bigger quantum computers, much higher performance? And then, what is the future of this technology going forward? How do you go from maybe a couple dozen qubits to hundreds of qubits? And one of the ways we can do it is just utilizing what we've seen before. So if you have a finite number of laser beams, can we actually move the qubits in and out and actually scale the system to be a little bit larger? And this is, as you've seen, we already know how to shuttle things extremely well. So that's one way to continue to put more qubits onto a single chip. What is actually even more interesting is I showed you the mechanism that we use to manipulate ions and coalesce them into chains. But with that, you can actually start to support multiple chains on a chip, which means that if you have a finite size quantum processor, you can put multiple of those processors onto a single chip. Okay? So that is supported by what we call the shuttling process that you have seen, where we are physically moving ions from one location to another to try to bridge communication between multiple chains in the system. And then the final, in our mind, the grandiose scale of getting to a much larger scale is analogous to how we build the very large classical computers today. We don't actually make silicon chips that are huge. What we do is we build a lot of little boxes, computers in a pizza box, and then we stack them together in a data center, and then that's how we make the most powerful classical computers. So here the process is we would build a large number of these relatively small and compact quantum computers, and then we will connect them together with a photonic network. And here, the entanglement between the ions is mediated by single photons that these atoms emit. And then by interfering the photons, you can create entanglement between the atoms. And by putting a bunch of these units through an optical cross-connect switch, you can actually generate entanglement between any pair of these units in the system by directing the photons from those pairs to an interfering interferometer on the output. So with this architecture, you actually have a flexible and cross-connected multiple quantum computers, and this is how we expect to scale our system into the future. Now, this kind of photonic interconnect, the basic principles were first demonstrated in Chris Monroe's lab in 2007, and that's almost 14 years ago. And over the course of the last 14 years, we have improved the entanglement generation rate by about a factor of 100,000, by about 5 orders of magnitude. And I think if we can push the technology just a little bit more, we can get to a level where the communication rate is starting to be comparable to the local gate speeds, and that will start to make the system much more practical going forward. So I think there's just a little bit of engineering push that's left to make that system a practical reality. So we're going to be continuing to pursue that as a system architecture. Now, in order to do this, in order to get to this point, each of those red boxes, which is a quantum computer, they cannot remain these big, large optical tables. So we actually have to start focusing on making your quantum computer a lot smaller, okay, and much more manageable. So that's some of the work that we have been doing at my research lab at Duke University. So I'm going to share with you some of the interesting work that we have done. So this is actually a standard example of how optical systems are set up in a typical atomic physics lab. You can see that there's a laser, there are some fibers, there are a bunch of optics that supports a specific function. But one of my colleagues, Dana Anderson at Quanta and University of Colorado, said if you know exactly what you want, you can make it really well. So what we have done is we have taken a typical optical layout like this and defined its optical function, and we started to compactly design them into smaller boxes. And here, all the optical layout is perfectly simulated, and then we actually integrate them onto a very compact box. And it turns out that if you have to tweak this optics every day, this one we haven't tweaked it in 2 years. Right? So the mechanical stability, optomechanical stability of this system is actually commercial grade, I would say. We made a little bit more effort and put probably about what used to take an entire optical table full of lasers onto an instrument rack. This was actually done by Professor Chungi Kim, who is now at SKKU. And he put all of the lasers that we need to trap and operate an ion-trap quantum computer into a rack. You can see that many of the components actually are now based on fibers. And then it has a couple of racks of this compact laser optics design. And of course, we use commercial instrument rack-mounted laser systems to operate this. Now, the next question is our vacuum chamber. And you can see that a typical UHV chamber that's needed to trap an ion is relatively large. It's typically a few liters. It takes months to build and several weeks to bake. It's a very painful thing to do in a lab. But what we have done is we've actually pulled all of the unnecessary stuff out of the vacuum chamber and only left a trap, an atomic source, in the vacuum chamber. In order to do that, we actually had to build a much bigger vacuum system. This is something that we built in collaboration with Quanta. This is $1 million vacuum chamber, but this is more of a facility. And what we do is we use this facility to create these little tiny packages. We put the trap in, we put the lid in, and then we seal it in vacuum and pull it out. And then at the end of the day, this allows us to build these very compact vacuum packages. So this is our actually latest vacuum chamber. This paper is actually published now. And here, the UHV chamber for ion trap is only about 5 centimeters on a side. Okay? Instead of this big, large stainless steel chambers, we now have this tiny little chambers. If you put it on an optical table, you can see that this is the size of a keyboard. So that's your vacuum chamber. And we have a bunch of optics around, which we haven't made an effort to miniaturize here, so that we can actually load that ion. And we can actually load ions, and they're very stable. So we decided to take the next step. With that kind of a vacuum chamber, what can we do? And we actually shrunk the box that you used to see, the 1 meter by 1 meter box, into something that is about 30 to 35 centimeters on a side. And then this is our latest ion trap system, where we have a vacuum chamber on top. All of the laser lights that's needed to trap the ions are brought through optical fibers. This lower level, this is entirely for imaging the ions and so on. And we haven't made a lot of effort in trying to make that very compact. But this system is working very well. So now you can see that the experiment really is fitting on a size that you can literally carry in your hands. So we do believe that we can actually push this further with this compact vacuum technology, and eventually, shrink the quantum computer down into something that could be mounted on a rack. Of course, we'll need to support a laser system to actually operate this thing. So if you look at the technology evolution of a trapped ion quantum computer, we started from something like this just 5 years ago. And then the first generation systems that we built at the universities, and also the ones that's in service at IonQ, is probably something that's on the order of a meter cube. Right? But we've been making a lot of progress since then, and today we actually have this box that's a meter cube is now probably about a foot by foot by foot, maybe 30 centimeters on a side. So we shrunk the volume of this thing by about a factor of 30 or so. And then what's really intriguing is last year there were 2 groups, one from MIT Lincoln Labs and another one from ETH Zurich. They actually put all of the laser beams that are needed to trap an ion onto the chip itself. So this chip that they demonstrated is an ion trap chip, but it also has integrated optics underneath. So you can imagine a situation where all of the things that are in that box can eventually be moved onto a chip. So that technology exists today, and therefore I think we can imagine a future where an ion trap really gets very compact. Right? Maybe not all the way down to a cell phone size, but certainly we can build it onto an instrument rack size ion trap quantum computers. All right, with that, I'd like to highlight that today there is an availability of fully connected programmable quantum computers, and that allows us to actually start making some progress on algorithms. And there are quantum machine learning, chemistry, and QAOA algorithms that are currently being demonstrated on the Mnist machines. And then the early implementation of very practically useful applications is really stimulating the potential for a commercially viable applications in quantum computing. And I think we're on track to reach commercially useful applications, certainly within this decade and hopefully sooner. So I'd like to thank my collaborators over the years and my colleagues at IonQ. Thank you for your attention.
Thank you, Jungsang. So here I see a question in the Zoom chat. So what's the maximum number of ion per chain? So is it limited by the phonon coupling, or what's the main trick to increase it? So related to that, do you have any sync problem when you want to connect module to module with photonic chains? So what's the maximum number of ion per module, and how to connect them?
Yeah, so that's a great question. Right now, in a chain, we have looked at a few dozen, maybe somewhere between 1 to 3 dozens is kind of where we are. And it does not look like our gate starts to slow down. Now, we are also learning that there are some physics reasons, like axial modes and things like that, that will eventually limit the size of the chain that we can use. And there are some recent papers from Chris's group that highlights that. So I think it's practically, we're probably going to be limited by somewhere between 2 to 3 dozens, maybe somewhere between 15 to 35 is kind of where we'll end up. And then how many of those chains you can put into a chip, I think it's a matter of technology. You need more complex traps, you need to figure out how to bring all the beams in, then I think we can make them. So the question is, can we develop a technology where we can put, say dozens of these chains into a single chip? And I think that the technology can be developed to get to that point, because at the end of the day, the real volume of your qubits is really small. And then the photonic interconnects, I think once we can establish that, the number of quantum computers you can connect through a photonic interconnect, I think will eventually be limited by the size of the optical switches you can build. And the largest optical switch that's been ever built has about 1,000 optical ports. That's something that I actually personally built. So I know the technology is there. So that will hopefully get us to, maybe hundreds of thousands of qubits in a single system over the course of the next 10 years or so.
Okay, is there any question from the floor? Okay, so we are used up the time. So
Okay, thank you.
yep, we just thank the speaker again.
All right, thank you.